So this video, I'm going to talk about the distribution of sample means. I'm going to emphasize that this is one of the most important chapters in the book and one of the most important online lectures. Not because you're going to be actively using the information from this chapter. In fact, it's almost the opposite. The information from this chapter is important for the intellectual foundation of the inferential statistics that we'll be looking at. It's important conceptually to understand where the inferential statistics techniques come from. But it's not information that you're going to be actively using. It's a little bit difficult to understand. It's a little bit difficult to use, but once we get into it, hopefully it'll make sense. Okay, so first we'll talk about why are we using the distribution of sample means. We'll talk about the definition and describe it. So the goal for statistics in part is we want to make estimates about the population based on a sample. We know that sampling error is always a problem. Now we will focus on how to estimate sampling error. And just a reminder, sampling error is the amount of difference between a sample mean and the corresponding population parameter. Okay, to estimate sampling error, we must start with a theoretical distribution. Every time we do research, we work with the sampling distribution. We want to determine where our sample mean lies in the sampling distribution. We can ask the question, so related to stuff we were doing in the last chapter, does it lie in the body or the tail? The distribution of sampling means is the distribution of the means from all possible random samples of a given size. So what does that actually mean? Let's go through it. So let's begin in this example that we're going to go through by saying we have a population. The population is the people of interest. We don't have the population mean, but we are able to take some samples from the population and calculate the sample mean. So the numbers that I have listed below here are not raw scores taken to make a sample. The numbers I have listed here in this example are sample means. In other words, we took 10 different samples from a population. So we took a random sample from the population. It doesn't matter how many scores that we took, but we got a sample mean of 89. We did that again. We took 50 or 100 or whatever number of raw scores out of the population to make a sample, and the mean of those scores was 74. We did it again, and came up with these 10 sample means on this slide. So here we have graphed our 10 sample means. What would you guess is the population mean based on these sample means? So a good guess that you could do is to take the mean of these separate sample means, and that's a good guess, but that itself is going to be subject to sampling error. So the mean of these 10 separate means is 85, but there's still probably some sample error there. But what if we take thousands of different samples from this population? You'll always get something. Well, under specific circumstances, in most circumstances, you'll get something that looks like the graph on the bottom right hand corner. All those different samples are going to pile up on top of each other around a certain number. In this case, it's 80, with a standard deviation of 20. Does this mean that the population mean is 80? So all these different samples are piling up around 80. What does that mean? Let's look at some characteristics of this distribution of sample means. By the way, the graph on this slide that we're looking at is a distribution of sample means. That's literally what the term means, is you take all the different sample means, group them together on one graph to make instead of having a distribution of raw scores, which is what we've typically looked at, we can make a distribution of the sample means. So some characteristics of the distribution of sample means. One is that sample means are variable. If two or more samples are selected from the same population, the two samples will probably have different means. This is pretty intuitive. If I were to select 3 random students from this class and take a mean of their height, you can imagine that if I did that 2 or 3 times and took 3 students each time, that the mean height that I'm going to get from all those measurements is going to be different every time. So if the population is this class, and I take samples of 3 students and take their height, the height is going to be different every time. There's a little bit of error there. 2. Although samples have different means, we expect the sample means to be reasonably close to the population mean. And this causes the pile up around the population mean that we saw in that graph earlier. The distribution of sample means tend to form a normal distribution with an expected mean of the population mean. So the expected mean of the distribution of sample means is the same as the population mean. Third is that any individual sample mean will most likely not be identical to its population mean. There will be some error between the sample mean and the population mean. So how do we measure? So remember when we were talking about standard deviation. Standard deviation is how much deviation we would expect between a raw score and the distribution's mean. We're going to introduce a new term now called sample error. Standard error. Standard error measures the expected typical deviation from a sample mean and the population mean. So standard error, you should recognize immediately, is pretty similar to standard deviation. But whereas standard deviation, we have a distribution of raw scores in which we're using standard deviation, standard error is applying to a distribution of sample means. So it's good to know that those two things are similar. They have similar uses. Even mathematically, they're going to look similar when we see that in a minute. But they apply to two different types of distributions. Standard deviation applies to a distribution of raw scores. Standard error of the mean applies to a distribution of sample means. Okay. When we're dealing with a distribution of sample means, we need to understand the central limit theorem. Now, your book defines the central limit theorem as this. For any population with a mean equal to mu and standard deviation equal to sigma, the distribution of sample means for sample size n will have a mean of mu and a standard deviation of sigma divided by the square root of n, and will approach a normal distribution as n approaches infinity. Now, you can look that definition up in your book. It's in chapter 7, and I hope that you do take a look at this section in this chapter. But more importantly than that definition is what that definition means for a distribution of sample means. So that's what we're going to be going over in this video. You need to be able to answer these 3 questions about a distribution of sample means. All of these 3 questions follow from the central limit theorem. The shape is what? The central tendency is what? And the variability is what? So first, the central limit theorem helps lead us to this conclusion. If n is greater than 30, if there are more than 30 scores that we are able to use to make the distribution of sample means, then the distribution of sample means will be normal. Now, what does this mean? So it's easiest to show this graphic in the bottom right hand corner shows approximately a normal distribution of sample means. If we have a normal distribution of sample means, then we are able to apply standard error of the mean formula correctly. We are able to perform inferential statistics procedures that we're learning in this class on the raw scores and the distribution of sampling means. If the distribution of sampling means is not normal, then we are not able to perform these statistical techniques. We have to find alternative techniques, and this causes problems. The shape of the distribution of sampling means does tend to be normal, which is good. It is guaranteed to be normal if one of these 2 conditions is satisfied. If the population from which the samples are obtained is normal, then the distribution of sampling means is guaranteed to be normal. And if the sample sizes we are using are 30 or greater, then the shape of the distribution of sampling means is guaranteed to be normal. So we need to remember those 2 conditions that guarantee that the distribution of sampling means will be normal. One is if n is greater than 30, and 2 is if the population is normal to begin with. Okay, what about the central tendency for the distribution of sampling means? The mean of the distribution of sampling means is called the expected value of m, and it is always equal to the population mean. So if we have the population mean or the expected value of m, we know that the other one is going to be equal to that. And so I skipped over median and mode. Not as important, but just like a regular normal distribution, the mean, median, and the mode are all expected to be the same score, although we won't have to do much with that information right now. And so, third question, we know about the shape, we know about the central tendency, now we need to know the variability. What is the standard deviation of this distribution? Well, it is actually a standard deviation of a sampling distribution. And what this actually gets us is the standard error of the mean. It is the average distance of sample means from a population mean. When we talk about sampling error, you might hear me and you might see in your textbook later on in this class sampling error and standard error of the mean used in place of each other. For most purposes, those can be used interchangeably in a lot of contexts. I'll remind everybody again that when we're dealing with individual scores or raw scores, we calculate standard deviation. When we're dealing with sample means, we calculate standard error. So those are, I keep repeating that because those are really easy to get confused with each other. Remember, the symbol for the standard deviation of a population was just sigma. The symbol for standard error of a distribution of sample means is either sigma capital M or sigma x bar. The capital M and the x bar just are used to symbolize the mean. So the standard error of the mean is determined by two factors. One is the variability of the raw scores, and two is the size of the sample. So here's the equation for standard error. The equation for standard error is equal to standard deviation divided by the square root of n. So the biggest difference here between standard error and standard deviation mathematically is that standard deviation is used in the calculation of. Okay. So notice, kind of following from this, that if we have a higher standard deviation of the raw scores, this corresponds to a higher standard error. Now, standard deviation of the raw scores is not something that experimenters or statisticians can control, but something that statisticians or researchers can control is the size of n. So the number of scores that go into the sampling distribution of the mean, or that go into the sample means. As n increases, this causes the standard error of the mean to decrease. So we'll talk about soon, especially in the chapters on t-test, of why you would want the standard error of the mean to be lowered. And the way that we can, as the statistician or the researcher, lower the standard error of the mean is by increasing the n. Okay, so this is an example of a typical distribution of sample means. Each of the boxes on the top graphic represents the mean obtained for one sample. So the distribution of sample means for random samples of size 1, size 4, and size 100 obtained from a normal population with mean equal to 80 and standard deviation equal to 20 are represented on the bottom part of this slide. So notice, if we have the same population at the top, we can get wildly different distributions of sample means at the bottom. And what is the thing that we're able to change between these three graphs at the bottom? And that is the number of scores that go into a random sample, or n. Notice that if we use a higher n, then this kind of brings the body, this kind of shrinks the body of the distribution and pulls it inward. Graphically, we're showing here, progressing from left to the right, what I was talking about in the previous slide, and that is that the standard error decreases with increasing n. So here is another view mathematically of the calculations that go into the standard error of the mean for each of these three. Notice again, what's changing is the denominator. That's where n is. Okay. Here's another kind of display of the relationship between the standard error and the sample size. As the sample size is increased, there is less error between the sample mean and the population mean. Another way to think about this is, so why should it be that the error between the sample mean and the population mean decrease as we sample more people or whatever else is being sampled? I think of it this way. If we have 10,000 people in a population and we sample 10 of them, we're going to get an estimate of the population parameter, but it's not going to be a good estimate. If we sample 1,000 out of 10,000, chances are that's 10% of the entire population. We're going to get a more representative sample statistic that's going to be closer to the population parameter. If we sample 9,000 out of 10,000, it's 90% of the population. We're going to get a sample statistic that is very close to the population parameter. If we were able to measure all 10,000 of the population, we would get an estimate. Well, we wouldn't have an estimate. We wouldn't have a sample statistic. We would just have the population parameter. It would be equal. So I like to think of it that way. The more people from the population we are able to sample, the more representative the statistic is going to be in general. So let's connect it back to z-scores. So remember in previous talk, we know that we need to use this information about the distribution of sample means with z-scores in order to start talking about hypothesis testing. So how does this topic connect? Z-scores can be used on a distribution of sample means to estimate how close our sample is to the actual population. So we can use z-scores in this case. We can use z-score concept to find out if our sample mean is similar to the greater population mean. We could call this the z-score for sample means. It is the basis of the t-test, which is where we're starting our talk of inferential statistics. So we can answer this question. Is our particular sample mean in the body or tail of a distribution for a distribution of sampled means? This is a really powerful tool that we're about to learn. So when we talk about z-scores, if I just talk about z-scores by itself, z-scores can be used on raw scores. That's what we've been doing. But we can do a z-score test for sample means. It is going to look something like this. So notice that the regular z-score equation has been modified. Instead of having standard deviation in the denominator, we now have the standard error of the mean, which is equal to the standard deviation divided by the square root of n. So this is preparing our z-score test for sample means. A z-score can be computed for each sample mean. The z-score indicates where the specific sample mean is located relative to all other sample means. This allows us to show the probability of a specific sample mean as defined as a proportion of all the possible sample means. Okay, so just like z-scores indicated location above or below the mean and the distance from the mean, we can do that here with distribution of sample means. Except now our numerical value indicates distance in terms of standard error, whereas before it was in terms of standard deviation. Alright. The z-scores that we find are, again, used to obtain probabilities. These procedures although conceptually different from the procedures for z-scores and raw scores, procedurally, when we're actually computing these, it's almost identical. Now, remember why it was important before that we have a normal distribution of sample means, and here is where we connect to that. If we have a normal distribution of sample means, we are able to perform these z-score procedures. If our distribution of sample means is not normal, then we're not able to use the z-score procedures at all. Okay, let's quickly go through an example using the standard error of the mean. So let's say we have a population with a standard deviation equal to 30. On average, how much difference should exist between the population mean and the sample mean for n equals 4 scores randomly selected from the population? So take a second to pause and do those calculations. And that example was pretty easy. We should come up with 15. Okay. On average, how much difference should exist between the population mean and the sample mean for n equals 25 scores randomly selected from the population? And again, this should be equal to 6. You can see the calculations on the screen. Okay, here is kind of working backwards. For a population where the standard deviation is equal to 20, how large of a sample is necessary to find the standard error of the mean less than or equal to 5? We can work backwards here using the same equation to find that n must be greater than or equal to 16. Let's move on to an example using z-scores. So read this question, pause, and then let's go over the answer. Okay. Using our z-score equation for the distribution of sampling means, we can plug in these values to find the standard error of the mean equal to 5. Then we can plug in that value into the z-score equation to find a corresponding z-score of -1. Okay. What if we ask the question, we have a random sample obtained from a normal population. We want to know, is this a fairly typical sample mean or an extreme value if n equals 4? Now, there are several ways to define typical or extreme in the course. A good rule of thumb is that a typical score is one that falls within 1 or 2 standard deviations of the mean, or within 1 or 2 standard error of the mean. So pause and see if you can calculate this problem. Okay, let's look at n equals 4 first. So we can calculate, plugging in these numbers, we get a z-score of 0.75. 0.75 I would generally consider a typical sample mean. It's within 1 standard error of the mean. It's very close. What about n equals 64? In this example, I noticed that we still have n equals 4 at the top. We can ignore that. It was supposed to be n equals 64. We actually get a z-score of 3.0. This we would regard as an extreme sample mean because it's much further than 2 standard deviations out. Okay, let's go through this example. What if we have the scores on a standardized mathematics test for 8th grade children in Newark State? They form a normal distribution where the mean is equal to 70 and the standard deviation is equal to 10. Using this information, let's answer some questions. So, what proportion of students in the state have scores less than 75? If samples of 4 and then 25 are selected, what proportion will have means less than m is equal to 75? So take a minute to pause and see if we can go through these example questions. Okay, in order to find what proportion of students in the state have scores less than x equal to 75, notice that we're dealing with raw scores here. So we're using the original z-score calculation that we learned a couple chapters ago for raw scores. So we calculate the z-score, and then we need to calculate the proportion based on the z-score. And using the unit normal table in the back of the book, we find a proportion of 0.69. Alright, what about these problems here? Obviously dealing with the distribution of sampling means. We use our z-score equation for the distribution of sampling means. And first, we find a z-score equal to 1.0. Using the unit normal table, that matches to a probability of 0.84. We go through the same procedure for samples of n equals 25. And we find a probability of 0.99. And I'm going to end this video with a quick checklist. If you're able to accomplish the following things without using the book or notes, then you have a good beginning grasp on the distribution of sampling means as we're using it in the next couple of chapters. One is, can you define the central limit theorem, or give the 3 things that follow from the central limit theorem that we talked about in the video? Can you define the distribution of sampling means, either visually or with words? What is the formula for the standard error? How is it related to, and how is it different than, the standard deviation? Can you give the formula for z for sample means, and how is this different than the formula for z for raw scores? Why do we use the distribution of sampling means? And then finally, can you perform the types of problems found in this video and in the textbook? Make sure to communicate on Blackboard if there is anything unclear about this lesson. Make sure you're keeping up with the book chapters. Thank you for watching.